Okay, welcome to the next video on surface processes. This is on soil. Soil is an incredibly important part of our Earth's surface. So what is soil? Soil is ultimately a component of the regolith that can support the growth of plants. So what's regolith? Regolith is everything that isn't bedrock. Bedrock is the material that's actually attached to the crust, whereas regolith is everything that's loose. So mostly when we think about regolith, it's just sediments. They're pretty much the same thing, except that we wouldn't call a boulder to be part of sediments. It's just too big. But we would consider it part of regolith because it isn't ultimately attached to the crust of Earth. Now, what makes soil special regolith is that it can support the growth of plants, which is why this particular video is subtitled, it's a home for plants, because that's what makes a soil soil. Soil is a home for plants. So soil is made up of various components. Important components include air, water, mineral matter, and organic matter. So this is a diagram, this is a pie chart of the components and their proportions that make up a really good soil. So let's take a look at this. For one thing, you notice that the graph is divided into half air and water and half mineral matter and organic matter. Now let's talk about the half that's air and water first. Notice that there's arrows going in two directions. What that means is that it's not a constant 25% air and 25% water. What that means is that instead it's about half pore space. There's space between the individual grains of soil that allow it to become both air and water. Now if you pour, for example, you water your garden, that 25% will go all the way up to 50% if you really soak the soil. On the other hand, if it's a drought and you don't water your soil at all, it'll end up being 50% air. So it'll be very dry and crumbly, but it'll be mostly empty space. Now let's talk about the half that is an empty space that can be air or water. 45% of that, the majority of that, or 45% of the soil volume, is made up of mineral matter. What they mean in the book by mineral matter is broken down rock. So that's 45% of the volume of soil is broken down rock material. And then 5% is organic matter. So what's organic matter? Now I know some of the people who are watching this from this area are farmers, and they can imagine really easily what that organic matter is. It smells great. That's right, manure. Manure, feces, dead animals, dead plants make up that 5% organic matter, and that's utterly essential for supporting good and healthy plant growth. So let's talk a little bit about soil texture and structure. Soil texture is the range of sizes that are in soil, and there's three major sizes: sand, silt, and clay. Now in this area, much of our soil is made out of a sediment type called till. So we actually have soil that has gravel-sized particle in it. But that's not very normal. In most good soils, the big three are sand, silt, and clay. Now a soil that's ideal for growing plant life, particularly in your book it talks about just plant life, and I've left it that way here. But when we mean good for growing plant life, we mean good for growing plants we want to eat, is loam. Loam is the ideal texture for most crops. So what's a loam? So we have this diagram of soil texture, and it's a funny kind of diagram because it's going in, it looks like it's going in all directions. So I'm going to go to your book, I'm going to blow up the video and go to your book and explain how to read this diagram. So, just a second. Soil profiles, here we go. So here's the diagram on page 106. It's right here. Now these kinds of three-point diagrams are common in geology because a lot of things in geology are made out of three things. So for example, granite is made out of three minerals. Soil is made out of three major sediment sizes. Now how you read this is these numbers along here are facing this direction, so you read the lines going this way. Over here, these numbers are facing this direction, so you follow the lines this way. And down here, these are tilted in this direction, so you read the lines this way. So let's see what a loam is made out of. That's this point right in here. So this loam right here, if we follow the lines, we can see that if we go out from the center, a loam is 40% sand, which is the largest grain size, 40% silt, which is the medium grain size, and if we go out this way, 20% clay, which is the very smallest grain size. Now each one of those has a different role to play in the sediment, in the soil. So if you have a very sandy soil, that's very good for drainage. So the soil that my house is built on is very, very sandy. And that's because it's from an ancient beach from back when the glaciers were around. So when there was a big glacial lake, my house was beachfront property. It's not anymore, but it was back then. And so I have a really, really sandy soil. That means that my soil is very good at drainage. Now, clay in a soil does a good job of holding in water. So you want a good balance of clay, silt, and sand because you don't want the water to run straight out. You want it to be partially held in, but you don't want it to get what's called waterlogged. In other words, for it to get totally soaked with water. If you had a soil that's just clay, that kind of soil gets waterlogged really easily. So soil structure is how the soil particles clump together to give the soil its shape. So when you roll it in your hands, what you see. So four major basic soil structures are platy, prismatic, blocky, and spheroidal. And these just have to do with the shapes of the clumps as they fall apart. Now you don't need to know those names for the test, but you do need to know the difference between soil structure and soil texture. Now some major controls on the materials that make up soil. One big control is parent material. And there's two types of parent material. Residual soil, where the parent material is made from the local bedrock, and transported soil, where the parent material has been carried from elsewhere and deposited here. Now, residual soil because it's made out of broken down bedrock, it's made out of whatever material is local. So in this area, our bedrock is limestone. So the area that JCC campus is on and most of Jefferson County is made out of, the bedrock is made out of limestone. Now limestone, as we learned in the weathering lecture, breaks down really easily in the presence of acid and in rain. So what that means is that the bedrock dissolves very easily if it gets broken down. So in actuality, our soils aren't really mostly made out of our bedrock. Our bedrock instead dissolves completely and turns back into carbon dioxide. What our soils are mostly made out of is transported soil. So our parent material has been carried from elsewhere and deposited. In this case, our soil in this area is largely transported by glaciers. So we can have a huge range of soils. So if you go down, you have my area, which is near Thompson Park Hill, and then you have the area that's down in Sandy Creek. Those are both very sandy areas because those are right along the beachfront of the ancient glacial lake. You also have a lot of glacial lake bottom material, so that tends to be very, very clayey. If you head out towards Carthage or towards Gouverneur, you have a lot of drumlins, and that's a lot of tilly material. So you have a huge diversity of different sediment types because it was all transported and deposited by glaciers. But glaciers can deposit a whole bunch of different kinds of sediments, which we'll learn a lot more about when we talk about glaciers. Now time. Time is really important for all geologic processes, and the amount of time it takes a soil to evolve depends on the type of soil. So, for example, if you have a desert soil, that takes a really long time because in order, the same processes that are associated with weathering are associated with soil formation. You need a breakup of the rocky material, and you need the growth of plants. So a desert, because it's so dry, it doesn't have a whole lot of chemical or physical weathering occurring, and it doesn't have a lot of plant growth to help contribute to the organic matter. So a soil in a desert takes thousands and thousands of years to evolve. But somewhere more temperate and wet, like Watertown, it can take a few hundred years to make a couple of centimeters of soil. So the amount of time that's needed very much depends on climate. Plants and animals also play a huge role. So if you have the presence of worms, that's going to speed up the formation of soil, because worms leave behind worm poop, worm feces, which is also known as castings. Neat fact, in this area, Jefferson County and up into Canada, worms aren't indigenous. Worms aren't native to this area. They were actually all wiped out by the glaciers. So our soil formation is very, very slow, and we end up with really, really thin soils. All the worms that you see around you were transported in by the Europeans, either for farming or for fishing or other purposes, or just by accident. You know, so worms get into things and then they get out. Other ways that animals can influence soils is they can provide manure, in other words, fecal matter that helps decompose and form soils, dead, rotting plant material. Slope has a huge influence on soil formation. Soils are not going to form on a slope like this. The soil is just going to erode straight down the wall. Remember, erosion is the transport. We can also say that it undergoes mass wasting, goes straight down the hill. So the angle of the slope, if it's too high of an angle, you're not going to have soil formation. You're going to have the best soil formation in the valley, not at the top of the mountains. Tops of mountains, if anyone's ever been to the Adirondacks, tends to be bare, whereas it's in the valleys, that's where the good farming is. Also the orientation, the direction the slope is facing. So as we learned in our last unit, and as we learned in our meteorology unit, the sun is never directly overhead in Watertown, and it always is a little bit to the south. So in Watertown, because it tends to be kind of chilly and wet, it's really good to plant our plants on a south-facing slope because they have that constant sun exposure. Now that actually turns out to be the opposite in deserts. In deserts, because there's too much sun and too much heat, the best plant growth and the best soil formation tends to be facing away from the sun. So in the northern hemisphere, that would be on the north-facing slope. So this gives you an example of how we expect to see soil development and how topography, the shape of the land, influences soil development. So in the tops of mountains or on steep slopes, we expect to see a lot of bare rock. And that's one of the reasons we see it around here. We have a lot of exposed hills due to our tilted bedrock. When it became eroded by the glaciers, it formed like these really bare hills. Then we have these lower areas where all the materials deposited form these much thicker sediments, and that allowed for deeper soil formation. We also downslope tend to have a lot more water accumulate, and that's a very important concept that'll help you answer a lot of questions on the test. When I ask you a question, which way is a river flowing, or which way does the materials on the hill go mass wasting, or which way will you get the sediments deposited, it's all down. Everything falls down. So at the bottom of the hill, you're going to get a lot of soil formation because you have a lot of water flowing in there and you have a lot of sediments accumulating. Now, this helps form a soil profile. Soil profiles are formed from the structure of horizons. So those are zones or layers of soil that form in order. Now, there are a lot of different horizons, and if you want to read more about that, it talks about it a little bit in the climate regions, and you can also do it as compare and contrast for one of your questions on your unit journal. But the horizons that are common in temperate regions are the O, A, E, B, and C. So let's take a look at that. So the O layer is the loose and partially decayed organic matter. So if you look at the leaf litter on the forest floor, that's the O horizon. Or if you're just walking through a prairie, you're going to see a lot of tangled, dried up plants towards the bottom of the grass. That's the O horizon. It's just organic material. The A horizon is that dark, rich, organic layer just below the O horizon. And the O horizon and the A horizon together is what's called the topsoil. Now just below that is the E horizon. The E horizon happens because water flows down through the soils, and as it moves nutrients, it actually washes them out. Okay? The B horizon is the accumulation level. So as it gets washed from the top layers, eventually that water will reach the maximum extent that it normally infiltrates, and that will be your B horizon. Your C horizon is partially broken up rock material in the process of being weathered, and then underneath that is your unweathered parent material. That's your bedrock. Now in this area, we have a very good O horizon. We have an A horizon. We have no E horizon, no B horizon in most places. We have a nice C horizon, and then we have the bedrock. And this is because the bedrock's very close to the surface, and most of our soils tend to be fairly thin and fairly young. Now, in different climates, you're going to have different soils and different soil horizons. And once again, you can use this portion of the lecture to help you answer one of the journals. So in this case, we see an example of a soil in Puerto Rico and a soil in southwestern South Dakota. Southwestern South Dakota is a much colder, drier place than Puerto Rico, and that influences the structures of the soils that you see. Now, in different regions around the world, you're going to see different soils. I'm not going to test you on the soil orders, but you can use them in order to answer your question in your journal comparing the different soil formations. So, for example, in the tropical regions, you tend to have very, very, very deep soils, like oxasols, that are really, really deep, but they're really nutrient poor. So that concludes our little lecture on soils. I hope this was helpful, and I hope it helps you answer the questions in the journal.